All right. So now let's learn about resonance structures. What resonance structures are is just that you have, in short, the easiest way to describe it is that lone pairs can be transitioned into bonded pairs at the same time. And so these bonded pairs could also go back to being lone pairs. And so if we look at this in a structure, so let's go through an example of this. Let's look at an example of CO3 2 minus. And so if we drew this as a Lewis dot structure with its molecular geometry, we would have something that looks like this. We have a CO double bond, we have a single bond over here, and a single bond over here. And these lone pairs actually really matter in terms of drawing them, and their formal charges also really matter. And so in this case, our formal charge is that this is a negative charge, this is a negative charge, this overall has a -2 charge. What I mean by lone pairs and bonded pairs can be swapped over is that if you notice that all three of these things are the exact same thing attached to this carbon in the center. And so when you have things that are the same, they could all end up looking the exact same. As in, we notice that one of them is slightly different than the rest, which is this one has a double bond. What ends up happening is that all three of these oxygens could have that double bond. It's just it will have to shift everything over to draw that. So let's example, let's say that this is carb or oxygen 1, this is oxygen number 2, oxygen number 3. All three of these oxygens can have a double bond. And so let's say that instead our oxygen 1 has a double bond. How that happens is that this one of these lone pairs, let's just say this lone pair right here, gets migrated and pushed into a double bond over here. Let's do this in a different color so it's easier to see. So let's do this in red. So what I'm saying is these two lone pairs will get pushed over to making this quote unquote double bond here. Then what that causes is it pushes these electrons to then get pushed out to being just lone pairs out to here for this oxygen. And what that would look like is what we draw as resonance structures with two arrows. Is you have a carbon here. Now this one is just a single bond. These electrons don't get changed. But now these two electrons in this bond right here get pushed out to being this lone pair out here. Then over here, this oxygen, we originally had one bond, right? With our oxygen with our 6 electrons. And I'll draw the same ones over here. But now these last two over here get pushed over into this double bond. And now they form a double bond between this carbon and oxygen, between oxygen number 1 and the carbon. And now this second carbon now has a single lone bond. And so it's negative charge again. And then this one, we have not changed at all. And so we now have the same exact thing over here. This is still a negative. This is still oxygen number 3. And that overall has a structure of this, a 2 minus. But now since we notice that oxygen 1 and oxygen 2 both could have the double bonds, oxygen 3 could also do that as well. And so let's draw that real fast with another color. So let's go with blue. So what if oxygen 3 had instead the double bond? That means that one of these gets pushed down to here to being a double bond. And then one of these electrons now can't be a double bond and gets pushed back out to this oxygen over here. And so then how do we draw this over here? Oxygen right here is a double bond now to our carbon. And then our other 4 electrons do not get changed, and so they stay the same area. These oxygen number 1 now has 6 electrons. 1, 2, 3, 4, 5, 6. And now has a negative charge once again. This is oxygen number 1. This oxygen number 2, we've never changed at all. And so this will stay the same. 1, 2, 3, 4, 5, 6. Negative charge once again. Oxygen number 2, oxygen number 3. And so now we have drawn where all 3 of the positions could have the double bond. This is what we call resonance. The reason for this is that what ends up happening, I'll try to draw this in a completely different color again, is that all 3 exist at the same time. That realistically, that instead of it just being rotating between these three, is that in reality, the actual CO3 molecule looks like a combination or a hybrid of all three. And so at the same time, since these electrons can be shifted over to a double bond or out to a lone pair, and that these negative charges can be shifted between all three of your oxygens, right? So in this case, oxygen 1 and 3 were your negative charges. In this case, oxygen 3 and 2 were your negative charges. And in this case, oxygen 1 and 2 were your negative charges. Because these electrons could be moved throughout your entire molecule, we kind of describe them as a hybrid between all three of these, and that these electrons, I like to describe them as fluid. That these electrons can be moved and pushed around throughout this molecule depending on what is necessary. And this is what we call resonance, is that things can be pushed around, that these electrons can be moved, and that in short, this entire principle really matters, that lone pairs can be pushed over and be made into bonded pairs and vice versa, right? So these bonded pairs can be pushed out to lone pairs, just like how lone pair into the bond gets pushed out to a lone pair. And so those both had to happen at the exact same time in order for it to be a resonance structure.